Hello, dear students. I am Samir Velankar. I welcome all of you to this second video on binary heaps. In the previous video, we understood how to represent any array in the form of sequential binary tree, which is also called heap. And we understood what is meant by max heap and min heap. Now, here is the second video where I will tell you how to construct a max heap. Consider an array of 8 elements with values like 100, 50, 200 and so on up to 90. And you see that the indexes in this array have been begun from 1 and not from 0. Actually, 0th index is also there, but I am wasting it. I am not storing anything at index 0. Why? We will see that later. But the array has been indexed from 1 and it goes on up to 8. So there are 8 elements in this array and the values are shown 100, 50 up to 90. Now, what is our aim is we want to convert, read this sentence at least 3 times. I will read it for you. We want to convert the above array into max heap. I read it again. We want to convert the above array into max heap. This array drawn above should become max heap. What does that mean? Every parent must be greater than its children. What that means is this 100, the first element is the parent of 2 and 3, isn't it? You know where are the children of first element? 1 into 2 and 1 into 2 plus 1. So second element and third element are left and right child of first element. What we want is whatever you store here in the first element should be greater than its left child and also right child. Are you following? See now again, second element of this array, second element, where are the children of second element? Second element have children at 2 into 2, that is 4, and 2 into 2 plus 1, that is 5. In fact, fourth element is the left child, you know. 2 into 2 means left child, 4, and 2 into 2 plus 1 means 5, means right child. So this second element should have a value which is greater than 85 and 210. Only then it will be max heap because parent value must be greater than its children. Come again, repeat this. Third element you observe. Where are the children of third element? 3 into 2, that is 6. And 3 into 2 plus 1, that is 7. In fact, 3 into 2, that is 6, is the left child. And 3 into 2 plus 1, 7 is the right child of third element, isn't it? Now we want that value stored at the third element here must be greater than value stored at 6th place and 7th place. Only then parent will be greater than its children. Check it out again. 85 is the fourth value. Where are the children of this 85? Fourth element has children at 8 and 9. Ninth element is not there. But eighth element is left child of 4. So this eighth element should be in such a way and fourth element should be in such a way that fourth element parent must be greater than the ninth element. I hope you are understanding. And after fourth element, you see fifth element does not have any children because child of fifth element must be at 10, 11, isn't it? And 10th and 11th elements are not there. So we want this array in the form of max heap means we want to satisfy following conditions. You note which conditions must be satisfied. The conditions satisfied must be, as written there below, is A1, A1, first element must be greater than second and third element. First element should be greater than both second and third. Why? Because first element is the parent of 2 and 3. Also, second element of the array must be greater than fourth and fifth. Because you know 2 into 2, that is 4, is the left child, and 2 into 2, 5, 2 into 2 plus 1, I am sorry, 5 is the right child. So A2 must be greater than A4 and A5. Also A3 must be greater than A6, A7 because A6, A7 are the left and right child of A3, and A4 must be greater than A8. No question of A9. A9 is not there in the array. Ninth element is not there. If all these conditions are satisfied, then we can say every parent is greater than their children, and we will say that array is in the form of Max Heap. I hope you have understood aim of this chapter, aim of the video. Okay. Now, coming to the same facts which were discussed in the earlier video, you know that the above array shown can be drawn as a heap. How do you draw it in the form of a heap? Simply add the values 100, 50, 200, 85 in sequence from left to right. So what will be the heap? Will be, oh, I'm so sorry for this. Many times it happens with my marker. Okay. Now, how will you draw the heap for this? 100 will be root, first element. Now we are adding values from left to right in sequence, remember. So next value 50, second element goes to the left of 100, 200, third element goes to the right, and now the next position from left to right is 50's left. 50's left will become 85, 50's right will become 210, 200's left will become 30, 200's right will become 250, and 85's left will become 90. Sequence numbers in sequence from left to right as shown. Now this is a heap, you all know, or this is a sequential binary tree. But it is nothing other than the array. I proved it in the earlier video. It is same as array, drawn differently in the form of binary tree. Tell me what is your aim? Come on, tell me. First node must have a value greater than second node and third node, because first node is the parent of second node and third node. That is node number 2 and node number 3. What about second node, which I am right now encircling? Second node, which is storing 50, should be greater than fourth node and fifth node. Now you see fourth node is storing 85 and fifth node is storing 210. What do you want? You want that parent number 2, this second parent, must be greater than its fourth and fifth child. Similarly, third node, this third node, should be greater than sixth and seventh. Whatever value you store in the third node should be greater than sixth and seventh. And finally, fourth node, which is right now storing 85, should be greater than eighth node, which is storing 90. If you do all this, then only this heap will be called as max heap, because every parent will be greater than its children. Now, how do you do this? We currently have this heap. How do you convert this heap into max heap? Is you always start adjusting last parent first. Of course, you know now we have to do something with the parent values. We are interested that parent values must become larger than children. So keep an eye on all the parent nodes. Where are the parent nodes? First node is the parent. Second node is the parent because it has children. Third node has the parent because it has children 6 and 7. Fourth node is a parent because it has child 8. But after that, fifth, sixth, seventh, eighth are not parents. They are not having any children. They are leaps. So we have to adjust value of all the parent numbers being 1, 2, 3, 4. And the great idea is you always start adjusting value of the last parent first. Don't directly adjust value of the first parent, doing something like I will make this parent, first parent, larger than both the children. No, no, don't do that. You will start adjusting the last parent first, and the last parent is situated at 4. After this, no other node is parent. Every node is a leaf. So you start adjusting the last parent. What do you mean by adjusting the last parent is somehow, you make this parent greater than its child. So let's see what we have written till now. We have to adjust value of all the parents, so that each parent becomes larger than both children, obviously. Then only it will be max heap. The parent nodes are always considered from last parent node to first parent node. So we will start adjusting fourth parent, make it larger than its child, then go to third parent, make it larger than its children, then go to second parent, make it larger than all its children, all its all its descendants, and finally adjust first parent, make it larger than all its descendants. I hope you are understanding. So for the given example, where is the last parent? The last parent node is situated at position 4. This fourth node is the last parent. After that, all are leaves. Hence, we adjust value of the last parent, parent number 4. So let's see what is the procedure for adjusting value of the last parent. For that, I will just reproduce the same heap over here. I'm not doing anything, but I'm drawing the same heap shown above so that we keep consistency or we keep a continuation with our discussion. This is the initial heap that we have, isn't it? Now then, what are we doing? We are somehow adjusting value of the fourth parent. This fourth parent should become larger than eighth child, its children. Parent should be greater than its child. Who is the child of 85? Come on, 90. And we observe that 85, value of this parent, parent is 85, is less than the child value. But parent must be greater than child. So what we simply do is, we take this 90 up here and we say this fourth node should not store 85, this should store 90. Larger value will be shifted to the parent. And now easily you can see that 85, which has been striked from here, will now occupy the child place. So eighth position will store 85, whereas fourth position will store 90. Yes, you can say that we have swapped these two values, we have exchanged these two values, you can say like that. But technically speaking, we first pushed 90 up, 90 was pushed up, and then 85 occupied the 8th place. So what is the latest heap now? Fourth value of the heap is no more 85, it is 90, and 8th place of the heap is 85. So we have parent 4 greater than child 8. That means A4 is now greater than A8. Are you following? Are you following? This is nothing but A4. Fourth node is nothing but fourth element of the array, and eighth node is nothing but eighth element of the array. So are you understanding? This last condition that we wrote has been now satisfied. A4 is greater than A8. Okay, have patience, take your time to understand this. Now we say that parent 4 is greater than child 8, surely. Hence we proceed parent node 3. We know that we are going to go backwards, fourth parent, then third, then second, then first. We want parent node 3 must be greater than child 6 and 7. Note that this parent node 3 must have a value greater than 6th and 7th, isn't it? Okay, how do you do that? I will just produce the same heap here, which we have. The latest heap is 100 is the first node. Left child of 100 is still 50. Check the above heap. 200 is the third node. But the left child of 50 was 85, but now it is 90. The node number being 4. Right child of 50 was 210, it is still 210. Left child of 200 was 30, it is still 30. Right child is 250. So these node numbers are 5, 6, 7. And the left child of 4, which was actually here 90 was stored, now we have 85. This is 8th node. Okay, now where you should keep your eye on? We want that this third parent must be greater than its children, both its children. So what is the procedure? First, find largest child of node 3. Who is the largest child of node 3? 30 and 250 are the two children of node number 3, and 250 is the largest child. So 250, that is node 7, is largest child. Now you compare this largest child, that is 250, with the parent value, that is 200. Now you see this is the parent value 200 and this is the child value, largest child. Now you know that parent must be greater than child, but in fact parent is less than child, isn't it? 200, the parent here is less than child. So what you will do is You will simply send child which is larger at the place of parent. I hope you got this. 250 will occupy the node number 3. But then what about 200? Yes, 200 will occupy node number 7. Are you following now? Node number 3 is storing 250, which is greater than its left child. Left child is 30. Sixth node, isn't it? And it is also greater than its right child, that is 200, node number 7. Hence, node 3 is now greater than child 6 and 7. Simple, isn't it? Find out the largest child and put the largest child up to the parent if largest child is greater. So, now we have parent 3 greater than child 6 and 7. So now we proceed to parent 2. We are coming backwards, you know. Parent 2 must be greater than child 4 and 5. This parent 2 on which the mouse is hovering should be greater than 4 and 5. Okay, let's see. First of all, I'll draw the heap that we are having currently. 100 is still at root, first node. Left is 50, as you see above. Right child of 100 is now 250. Just check this. This is the change we did while adjusting parent number 3. Left of 50 is 90, the fourth node. Right of 50 is 210, fifth node. Left child of 250 is still 30, and right child of 250 is 200, the seventh node. And the left child of 90 is 85, eighth node. Okay, where will you keep your eye on? Your eyes should be on the node number 2, because we are now adjusting parent 2. We want somehow that this parent who is storing 50 should have some value which is greater than its left child and right child. Isn't it so? So let's see what happens now. Who is the largest child? First of all, find the largest child of second parent. Largest child is 210. Compare this 210 with the value of the parent. Value of the parent is 50. This is parent value and child value is 210. Now you know that parent must be greater than child. But in fact, parent is having lesser value than child. Then simply put 210. 210 at the place of parent. 210 goes at the second node. And where will 50 go? Obviously, 50 will go at the fifth node. Now you know that second node is 210 and it is greater than fourth and fifth node. And also, fourth node is still greater than eighth node. 90 is greater than 85. Good then. Now what we have is parent number 2 is surely greater than child 4 and 5. Also, we have parent 4 is still greater than child 8. Now we must adjust parent number 1. And you know parent number 1 must be greater than child 2 and 3. So let's do this. I will draw the heap that we have currently. 100 is still first node. Left now is 210. Observe the above heap. Right of 100 is 250. Okay. And left of 210 is 90. Right of 210 is 50. Just check it carefully. 30. Then 200 is the right child of 210 and left child of 90 is 85 with position numbers shown as 4, 5, 6, 7, 8. Now your eyes should be on node number 1. We want that this node number 1 should be somehow having a value greater than second and third. So you will find out the largest child. Largest child of node 1 is 250 and 250 is higher than 100, isn't it? So larger value up. So this first node is now going to store 250. Now where will you put 100? Wait. You will not put 100 at node 3 straight away. This is it. This is crux. This is core of this topic. You cannot put 100 at the place of third node. This will be wrong. Tell me, if you put straight away 100 blindly at third node, then who are the followers of this node? 30 and 200. Now how can be 200 at the child when 100 is at the parent? Are you following what I am saying? Parent must be greater than child. How can you put 100 at the third node? If you put 100 at the third node, then third node will be no more greater than 6th and 7th, because 200 is sitting at the 7th node. So 100 cannot go at the third node. Why? Because there is a largest child 7 which is greater than 100. So 200 gets shifted up. 200 will occupy the place, third place. Now third place is 200. And now still 100 is waiting, isn't it? 100 is waiting for a place. Now 100 finds its place at seventh position because seventh position does not have any followers. So 100 goes at seventh place. Notice first element is now greater than second and third. Second is greater than fourth and fifth. Third is greater than sixth and seventh. And fourth is greater than eighth. Now check the above heap. Every parent has a value greater than child. Hence, the heap is now max heap. By the way, what are the array elements? Read the array elements in sequence. What is the first node? 250. See the first node? It is 250. Second node? 210. Third node, node number 3 is 200. Node number 4 is 90. 5, node number 5 is 50. Node number 6 is 30. Node number 7 is 100. And node number 8 is 85. Now you notice all these values, are in the form of max heap because every parent is greater than its children. All right. Let's revise this very quickly. I'm using one array. Even I don't know what I am drawing. Let's say I have an array like this: 10, 8, 20, 25, 9, 45, 6, 86. Then we have, let's say, 20. These are the array elements indexed from 1. Indexed from 1. Okay. Somebody tells us convert this into max heap. Now, first of all, what is the initial heap? Initial heap is values added in sequence from left to right. So I'm just adding these values in sequence from left to right to get a sequential binary tree, which will be called as heap. But this is neither max heap nor min heap. We want to convert this heap into max heap. So what will you do? Start with last parent. Where is the last parent? Yes, of course. Last parent is at fourth node. After this, none of these are parents. All are leaves after this. So we have to adjust the fourth parent. Now fourth parent must be greater than both the children. Check the children of fourth node are at 8 and 9 and the largest child is 86. But 86 is greater than 25, parent value. So 86 will be shifted to the parent. So fourth node will now store 86 and 25 will simply go at 8th position. So now what is the latest heap that we have? The heap we have is 10, 8, 20. Next value is 85 now. Be careful. Sorry, 86. 86 is the next value. Then 9. Then 45. After that 6. And the last values are, this is I think 25. Yes, 25 and 20. So this is the current heap. Now what will you do? You have adjusted fourth parent, isn't it? You know that fourth parent is larger than 86 is larger than both the children. Now you go back to the third parent. Third parent must be larger than both the children. So what will you do is you will find out the largest child among these two children. 45 is the largest child. Now 45 is greater than 20, the parent value. So 45 will occupy the parent place and 20 will occupy the child place. Now you see third node is having value greater than 6th and 7th. So what is the latest heap now? Latest heap now is 10, left is 8, then 45, then we have 86, 9, 45 is left now is 20, you observe the above picture, and we have 25 and 20 as left and right of 86. These are the node numbers. Keep listening very carefully. So now we should adjust the second node, isn't it? Second parent. We have just adjusted the third parent. Now second parent must be greater than both the children. Now watch. Who are the children of this node 2 right now? 4 and 5. Now who is the largest child among these two children? 86. But 86 is greater than 8, the parent value. So 86 occupies the parent place. Now wait. 86 has occupied the parent place, but what about 8? 8 was stored at node 2, isn't it? Note, This 8 has been overwritten with 86. What about 8? Where will you store 8? Don't be in a hurry to store 8 directly at node 4. You will go wrong. 8 cannot be stored over here, you watch. You cannot put 8 here. Why? Because if you put 8 at node number 4, you are going to spoil all the hard work which you did before. You know that fourth node must be greater than 8th and ninth. How can you put 8 at fourth node? Because there are 25 and 20 following it. So what you will do is you will again find out the largest child of the fourth node. Largest child is 25 and 25 is greater than 8. So 8 can't go at the fourth node. You will put 25 at the node 4. So node 4 will now store 25. I guess you are following it. 25. And now finally 8 gets a place at 8th place because 8th place is a leaf. No problem. No followers for this. So what is the heap right now? The heap right now is 10 is still first node. The left of 10 is now 86. Right of 10 is 45. Left of 86 is now 25, isn't it? And right of 86 is 9. Then we have 26, and left and right of 25 is 8 and 20. Now coming to the big point, we have just now adjusted second parent. Now finally we will adjust first parent. That is 10. This parent must be adjusted. Somehow the first node should have value greater than both the children. So what is the procedure? Just check. Who are the children of first node? 86 and 45. Take the largest child. And largest child you see is 86, which is greater than 10 parent value. So shift it at parent. So the first node now no more is 10. It is 86. Now wait a minute. What about 10? 10 has been scrapped. 10 must be stored somewhere, isn't it? Don't be in a hurry to store 10 in the second node. If you store 10 in the second node, then all the hard work you did for adjusting second parent will be lost. If you store 10 at second node, then the second node won't be greater than fourth and fifth because 25 and 9 are sitting down below. So what you do before you store 10 at the second node, you ask who are the followers of 2, who are the children? They are 25 and 9. Then take the largest child of 2 and compare it with 10. And you know 25 is larger than 10, then 10 cannot become parent. 25 must become parent. I hope you are getting this. 25 now becomes parent. 25 sits at the second place. Now talk about 10. 10 is still waiting out. Can 10 go at fourth place? Because 25 has been shifted up. 10 still can't go at fourth place because note the followers 8 and 20. 20 is larger than 10. Then 20 goes up at the fourth node. Now finally 10 gets a place at ninth position. It is anyway leaf. So 10 goes at the ninth place. I hope you got this. So what is the latest heap that we are having? The latest heap is 86, then 25. Okay, wait a minute. The latest heap, just making some room, 86, 25, 45, then 20, then 9, then 20 again, I think. Yeah, 20. After that 6, and then left child of 20 is 8 and right child of 20 is 10. You observe every parent has become greater than its children. So this is Max Heap. I hope you have understood how to construct Max Heap from a given array. In the next video, we will solve one gate question, which is so easy now. Once you have understood how to construct a Max Heap, there are a lot of questions in every gate paper asked on Max Heap and Min Heap. Thank you very much.